Welcome to the Journey Chez Chem. Today's warm-up are some review for the assessment that's coming up. Please do the best you can, and we will review them in a moment. Number one is a volume problem. And initially, I like to write my balanced equation. And whenever we have a balanced equation, we know that we're going to have a mole ratio type of problem. Well, I'm given 4.4 centimeters cubed of the water. And therefore, I must change my 4.4 centimeters cubed of water to decimeters cubed because standard molar volume is given in decimeters cubed. And therefore, I want to go to decimeters cubed and I want to cancel centimeters cubed. Let's do a little bit of review here. There are 10 centimeters is equal to 1 decimeter. And when I cube 10, I get 1,000. 1,000 centimeters cubed is equal to 1 decimeter cubed. That is my conversion factor. And I'm looking for decimeters cubed. So the 1 goes in the top and the 1,000 goes in the bottom. Now, in order to change my volume to moles, I need to use standard molar volume. And 1 mole of any gas is always 22.4 decimeters cubed of that gas. That is standard molar volume. Now, I'm going to moles of oxygen, and my balanced equation shows me there's 1 mole of oxygen for every 2 moles of water. And then I'm going back to volume. And I know that 1 mole of the oxygen is also 22.4 decimeters cubed of oxygen. Now, this problem is also asking for the answer to be in meters cubed. And therefore, my final step, I'm going to meters cubed and I'm going to cancel decimeters cubed. So again, let's look at this conversion factor. There are 10 decimeters is equal to 1 meter. And therefore, when I cube 10, I get 1,000 decimeters cubed. However, I'm going to write it in scientific notation because then I can do this problem in my head. It's one big, long conversion factor. You just gotta love those conversion factors. So let's look at this. And we see that our 22.4 cancels. And my centimeters cubed cancels. And my decimeter cubed cancels. And my moles of water cancel. And my moles of water cancel. I get moles of oxygen that cancel. And I'm left with what I'm looking for, which is decimeters cubed of the oxygen. You can do this one in your head. Let's look at this. 4.4 divided by 2 is 2.2. And I'm dividing by 1 times 10 to the 3. So this would be times 10 to the 0, minus 3, minus 3. And therefore, my answer is 2.2 times 10 to the minus 6 meters cubed. But we're not quite done yet. We need to look back at our original problem, and we had 5 significant digits because all of those zeros were significant. And therefore, my final answer is 2.2000 times 10 to the negative 6 meters cubed of oxygen. And that's just making sure that you're paying attention to those significant digit rules, and we're reviewing them all the time. Well, that was some fun, and we'll be right back. In number 2, we are determining both the volume and the density of methane under specific conditions. And there are several ways, as always in math, to do these types of problems. And most students prefer to go ahead and change my grams to moles. And I have 66.5 grams of methane. And 1 mole of methane has a mass of 16.0 grams of methane. And carbon is equal to 12, and there are 4 hydrogens, which is 4 times 1.0, and therefore I have 12 and 4, and I get a total AMU of 16.0. And when I do the math here, I get 24.1562 moles of methane. Now, because I am not given enough information to get a balanced equation, and I'm not changing from one compound to the other, I can go ahead and use the ideal gas law, which is PV equals nRT. And I'm solving for volume. Therefore, volume equals nRT over the pressure. Now, it would also be possible to go ahead and write grams over molecular weight here and then solve directly putting the grams and the molecular weight into this problem. However, it's more straightforward to see it in this form. And therefore, I have 4.1562 moles of my methane. And I'm going to use the ideal gas constant for ATM because I'm given a pressure in ATM. 0.0821 ATM liters per mole Kelvin. And the temperature is 16 degrees Celsius, and 16 degrees Celsius plus 273 is equal to 289 Kelvin. And remember, in gas laws, we always have Kelvin. And our pressure is 4.0 ATM. And when I do the math here, I'm going to get 24.6534. And I look back to my original problem and I want two significant digits. And because volume is one of the questions here, I want two significant digits. And that would be 25. The 6 is going to go ahead and round up the 4, and that would be 25 liters of methane. And then to do the density, I just go ahead and say 66.5 grams, which I am given in the problem, and I'm going to use the more accurate number in a calculation, and therefore I'll use 24.6534 liters, and therefore I'm going to get I'm going to get 2.6973, and I want two significant digits, and therefore the 9 will round the 6 up, and I will get 2.7 grams per liter of my methane under these conditions. Now that's how you do number 2. And now you will be able to review the answers of the review sheet with your facilitator. And tomorrow's a big day, so you make sure you understand the work that's on that review worksheet, and that gives you an idea of what types of questions you can expect. Well, that was some fun. Well, thanks for being here, and I can't wait to see you tomorrow.